Hello. All right. We got another chapter here. Let's talk about it. Chapter 7. So, chapter 7 is the sampling distribution, which is really the central limit theorem. But here's the deal, we're going to go over it formally in notes, but let's just give a breakdown of what's going on. Before, we were finding probabilities, and we can do it like height and weight. And I can find the probability that you are this tall, or the probability that you weigh this much, or between these two amounts. But at a certain point, I stopped caring about individuals. And what I want to do is ask a question. Maybe it's about height, maybe it's about weight, maybe it's a yes or no question. But I want to ask a question from a group. What's the probability this group weighs more than this on average? So now, instead, I don't care about your individual heights or weights anymore. I want to say this group of five, what's your average height? What's the probability that you have that average height? Is this just randomness, or is this too weird? What's going on? And that's how I want to analyze things. So instead of analyzing individuals, I'm analyzing groups. And from these groups, I'm collecting a mean, let's say. So now my random variable is a mean. So instead of having just some arbitrary mu, I'm having the mu of x bar, or the mu of p hat. That's what's going on now. I'm asking groups of people and saying, hey, you five, what's your average height? Okay, record that. You five, what's your average height? Record that. Record that next group of five, and that group of five, and another group of five. And then let's consider this average group, or average weight or height in a group of five. And let that be my random variable. And now this might seem like a weird thing to do, but it turns out it's very useful in a whole bunch of different scenarios that we will continue to analyze in this book. Right now, we're just going to deal with the probability. So now we're in chapter 7, section 1. And it says there, statistics such as X bars can be random variables. Because if I picked a random group of five off the street, I don't know what their average height is together, or average weight is together, or average IQ, or average test score. So by asking them and being like, wow, that's a very smart group of people, what's the probability that this were to be true? And I can go about that. So yeah, so that's the game here. As such, they have probability distributions associated with them. In this chapter, we focus on the shape and center of the statistics, such as X bar. We're going to focus on proportions also later. That's what that mu sub p hat is. Yeah. So the sampling distribution, the sampling distribution of the sample mean X bar is the probability distribution of all possible values of the random variable X bar computed from a sample size of size n, with the population mean mu and the standard deviation sigma. So again, just to be the most clear, and it's really awkward, this situation that we're dealing with. Before, I might find the probability x is below 6 foot, or x is below 200 pounds. But now I want to know the probability x bar is below 200 pounds. I want to know, hey, not what's the probability an individual is under 200? What's the probability the average of 5 individuals is under 200 now? So that's the difference. Okay, so let's continue to build this, right? The sampling distribution, this type of distribution comes from a list of sample sizes, list of sample means taken from many different random samples. Are we actually going to ask tons of groups of 5? No, we're not going to, but the data is going to be given to us. So it says now, suppose the weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46. So let's just highlight that. And a standard deviation 0.02. So to be clear, mu is 2.46 and sigma is 0.02. But now I want a group of 5 pennies. And we record the mean of those 5 pennies. And you can see here, now I do this, let's say 200 times. A group of 5 here, a group of 5, another group of 5, and another group of 5, and keep recording the average weights, the mean. So once I do this, I would have a new mean. Mu sub x bar equals something, and sigma sub x bar equals something. So before, this was an individual. And now this would be n equals 5. And we'd get a new value. If I were to throw all of that in the calculator, I get a different value. All right. So now this mean here, the mu sub x bar ends up being 2.46, and this sigma sub x bar ends up being 0.0086. Let me double check that value. I'm pretty sure I saw that. Yeah, 0.0086. So my mean, my mu sub x bar stayed the same, but my sigma sub x bar is very, very different. And now the question is, how do I calculate those? Because I'm still doing normal CDF, just like last chapter. But I need to calculate mean and calculate sigma. All right. But why do I care? Why do I care about a list of means? Well, let's think about weight. Weight, I think, is the easiest, or maybe height. So now, very current, why would I care about the height of a group of 5 people, the average height? Or maybe the average height of a group of 6 people. Maybe if I'm playing sports, a basketball team might jump into my mind and analyze, hey, what's the probability that they're getting that tall of a team? Or a volleyball team for a group of 6 people. But not all of us play sports, not all of us pay attention to sports, but something that many of us have used in our lifetime and will use. When would I care that my average weight is not too big for a group of, let's say, 10 people? Hopefully, we're thinking an elevator. I need to design this elevator with a certain average in mind, right? If I know there will be 10 people on this elevator, I need to, I want to care about, hey, what's the probability that the average weight is going to be above this? Because if it is above this, if the average weight is above that, then the elevator is going to fail. Same situation with a plane or a roller coaster, right? That's why there's weight limits to help control this probability, right? I can't have the weight be too high. So there's a whole bunch of different reasons to analyze averages like that. And the more we get into this, and the more if you were to expand and do your own research, you'll see this pops up a lot. So we care about means for a lot of reasons. So average weight on elevator or airplane. So what do we actually do? Suppose that a simple random sample of size n is drawn from a large population with mean mu and standard deviation sigma. Mu sub x bar will be mu. And sigma sub x bar, notice it got smaller. It's going to be sigma over square root of n. Sometimes the standard deviation of a sampling distribution is called the standard error. I'll continue to call it standard deviation, but just in case you read outside sources and find that out. There's one small caveat. we're not always guaranteed that X bar is normally distributed. So you can see here, finding probability involving X bar, I need to verify we're normal. Find mu sub X bar and sigma sub X bar, and then use normal CDF. Okay, now the question is, how do I know we're normal? We're normal when n is greater than 30, or the population is normally distributed. Normally distributed. And that's what this fact is here. If a population, X is normally distributed, or if a random sample, I guess, whatever. If a random variable, sorry about that, X is normally distributed, the sampling distribution of X bar is also normally distributed. Now, what I'll mention is we don't necessarily have good problems for this. Whoops. To verify we're normal. So it's going to be important to do, and we're going to be asked about it on a test. We won't really see it on homework and quizzes. So just something to keep in mind. This will show up on a test, not necessarily on a homework or quiz. Only on tests. Alrighty. Let's practice. The weight of pennies after 1982 are approximately normal with the mean 2.46. What's the probability in a simple random sample of 10 that we obtain a mean of at least 2.465? So what am I being asked? Probability X bar is above 2.465. Well, since it's X bar, I need to check. X bar is normal. Find mu sub X bar and find sigma sub X bar. Well, X bar is normal because the population is normal. Yes, population is normal. Mu sub X bar is just mu, which is, in our case, 2.46. Sigma sub X bar is sigma over to the square root of n, which is 0.02 over the square root of 10. And just putting that in our calculator. We get 0.0063. So now, to find my probability, it's just like chapter 6, except I calculated a new sigma and a new mu. Normal CDF, 2.465, 10 to the 99, 2.46, 0.02 over square root of 10. I put this in my calculator. Just like last section. And I get 0.2146, I guess. And that's the game now. Hopefully you understand the situation because it's an important situation for later in the class. But basically, it's normal CDF again, just with a couple extra steps. And these formulas are something to be on your note card, right? So it's not too crazy. So let's try it here. Right, let's try this example, read through it, and let's see how we do. I'm going to press pause. You should press pause too and really give this a go. So we went through the calculations, and hopefully we saw the difference in part B and part C, right? Careful, because they're often asked side by side, the probability of an individual compared to the probability of a group of people. So notice the language, the probability, the mean change time, which is why I knew it was X bar, where it was just the probability, the oil change. It should have been an oil change probably, but you get the idea. So that's all great there. So now we're exploring a different style of question. Instead of asking, people for a numerical answer, average test score, average height, average weight, average whatever, we're going to be talking about a yes, no question. Hey, do you believe in this? Or do you think this way? Do you have this quality? And then I'll record the number of people that said yes. So from this group of 10, I might get a 0.7. From that group of 10, I might get a 0.6, and then a 0.8, and a 0.5. And then those are my random variables now. And you might be able to imagine when this would be important. And hopefully you're thinking about voting, right? Finding the probability that a certain proportion of people think a certain way, right? We can do the polls early. That's what a lot of polling is. But anyways, this is still chapter 7, and it's section kind of 2 and 3 here. But anyways, a new parameter will assess or access, I think it's supposed to be assess, is population proportion. And we denote that P. So if 60% of people think this way, what's the probability that some percentage will think that? The sample proportion is P hat. Or you can see it there. Sample proportion is denoted P hat. And is given by P hat equals X over N, where X is the number of people that think a certain way, that have this quality, that said yes, that agree, and then N is just however many people you asked, right? Same situation. I ask a group of people and I care about what they think now. But the question is a yes/no question, or an opt-in, opt-out, success or fail is the idea. So let's start to play around with this, because it's building the same game, just with a couple new formulas. So it says in this university poll, 2008, 1745 registered voters nationwide were asked whether they approve of Bush's handling of the economy. 349 said yes. Obtain a point estimate, P hat. Sometimes this is called a point estimate. So P hat is going to equal X over N, which is 349 over 1745. Put that in the calculator, and we get 0.2. Beautiful. So for right now, we don't calculate P hat that often. We are going to use it every once in a while, but most of the time we're given P hat. So now, again, we're just going to mirror the section before this, the sampling distribution. Of the sampling distribution. Is that what we wrote earlier? I feel like something's a little bit off. Of the sample proportion. The sample proportion, P hat, is the probability of all possible values of the random variable P hat computed from a sample size N from a population proportion P. Right, and that's just like what we had here. Oops, sorry, jumping around a lot. Okay, there we go. And it says this type of distribution comes from a list of sample sizes. And we don't worry about that. What do we do with the sampling distribution of p hat? I think the reference here is usually talk about voting. Not always, but it is the most common situation to find probabilities anyways. So, when it gets down to it, the mean and standard deviation of the sampling distribution, mu sub p hat, turns out it's just p. Whatever p is, same thing. Standard deviation, sigma sub p hat, is square root of p q over n. And recall, q is 1 minus p. So finding probability involving sample distributions, exactly the same. Verify it's normal, find mu sub p hat, sigma sub p hat, and use normal CDF. To verify your normal, there's only one way. And it's different for each book, but the problems that we're going to do is going to be if NPQ is greater than or equal to 10. Alrighty. So let's see what a problem looks like. So according to a time poll conducted in June of 2008, 42% of registered voters believe that cat and dog couples should be allowed to marry. Suppose that we obtain a simple random sample of 50 voters to determine which voters believe that this should happen. It's a weird example. I did not write this example. Describe the sampling distribution. Okay. So first off, I guess we're trying to figure out, are we normal? So from this paragraph, hopefully you've picked up that P is 0.42 and N is 50. So notice the style of the problem. You know, in 7.1, we were given a mu and a sigma. Now all we're given is some percentage and an N. So now I'd want to find out, are we normal? So I'm like, okay, well, NPQ 50 times 0.42 times 0.58. What does that equal? 12.18. And that's greater than or equal to 10. So check, we're normal. Then mu sub p hat is p, 0.42. And sigma sub p hat, square root of 0.42. Well, we'll say PQ divided by N, square root of 0.42, 0.58, all over 50. So we try that, and we get 0.0698. So if we wanted to find the probability, that would be the mu and sigma I use. So hopefully that example made sense. Now we just need to use normal CDF. So let's read this example about overweight children, and let's see if we can get the answer. So I'll press pause and let you try to beat me to this. Please press pause here and give this a go on your own. It is important to try. All right. So there's the normal, or there's the first example. Hopefully you checked that we're normal, even if you didn't write it out in gold. You tried it or checked it. We found the mu and sigma, they're in pink. And then in that burgundy color, I found the probability. So B is actually the same question. But it feels weird because I didn't find the probability that it's a percentage. I said more than 24. But look what it says right there, 24 out of the 90. So can I convert that to a percentage or a decimal? Again, I'm going to press pause and let you finish the problem. So just think about that. But hopefully the work I did makes sense there. All righty. So hopefully you figured out we needed to calculate the p-hat first. Many problems on MyOpenMath are structured like this, so be on the lookout about it. And then you run it just like the part A with the probability there. So I hope this is clear enough. It's a tricky section. We have a little bit of extra time to go over it, so please take your time. But other than that, good luck. Remember to come see me in office hours or email me if there are any questions. All right, have a good one.